Well, hi again, this is Bob, and I'm over on the bottom of page 269. This is a very short topic. I'm calling this 5-2 Part 3. I mentioned that these are redos from something I did earlier, but they seem to have disappeared. And this is this last topic for 5-2. Is on expectation or expected value, and they tell us that this is used in games of chance and in the insurance industry. We're only going to take a look at one example, and this will not is not necessarily a topic that we're going to emphasize, but there are more examples if you're interested. And they show, well, excuse me, there's a couple of ways that we can do these questions, and there's a very good example problem that I'm going to do, and I'll stress both methods. Anyway, they tell us that the expected value, this is at the bottom of page 269, of a discrete random variable, which is what we've been dealing with, the expected value of a discrete random variable of a probability distribution is the theoretical average of the variable. And so what they're basically telling us is something that we've also seen already. Here's our expected value of x, but if you notice, it's equal to the sum of the x's times the probability of x. Okay, and remember that the capital E of x there means the expected value. And then on the top of page 270, they tell us the formula for expected value is the same as the formula for the theoretical mean. Anyway, what we're going to do is we're going to take a look at example 512, and we'll do it both ways. And this is about winning tickets, and they've sold 1,000 tickets at $1 each for a smart television that's valued at $750. What's the expected value of the gain if you purchase one ticket? Well, it might help to notice here that if you been to lotteries or games of chance or carnivals, that type of thing, or a raffle, right away we know that whoever is selling this or running the raffle or the game of chance, the television is cost $750, and they're selling 1,000 tickets at $1 a piece. So we know that whoever is running the raffle in a fair world would be looking to make $250 overall on the transaction. And that might be helpful to keep in mind. Anyway, there's two ways to set this up, and we'll look at the first one first that they show us, where we have we're going to find the probability of a win and a loss or lose. And we're going to call this the, try to use their format here, a gain, which is like our random variable x, and then the probability of x. Now, this is supposed to be an x here. Now, remember that you're paying $1 to play the game. So if you actually win the TV, you win $749, and you lose, if you lose, you're going to lose $1. Okay, so if you notice there, we've got a random variable x that's a minus. Now, what's the probability of winning? Well, they sold 1,000 tickets are sold, and we'll assume that each one is sold. So you have one way, and we recall that a person buys one ticket, so you have one way out of 1,000 to win, and you have 999 ways out of 1,000 to lose. So as we've seen before, our expectation in this case of x which means, remember, this is phrased as what's the expected value of the gain if you purchase one ticket. We've seen this before. It's the sum of the x's times px. In other words, this would be our win, which would be 749, and its probability is 1 out of 1,000. And then I'll use a plus a minus 1 over 999 over, excuse me, it would be 999 over 1,000. Let me just start that again up on the top of the next page. Thinking and talking at the same time didn't make it that time. Okay, so we had a gain of 749, and that probability is 1 out of 1,000. And then I used a plus minus 1, and I just like to put that in parentheses so I don't get it mixed up. And that's going to be times 999 out of 1,000. In other words, this is our gain part here, or our win, and this is our lose. So we would end up with 749 over 1,000 minus 999 over 1,000. And when you do that, you end up with, I believe, 250, minus 250 over 1,000. But the book doesn't show it, so I'm going to double check it just to make sure. Yes, we end up with minus 250 over 1,000, and that's the same as 1/4, or just minus, remember we're dealing with money here, minus 25 cents. So, to interpret this, there's a couple of things to think about. One is that you can only win the television set, which would net you a $749 gain, or that you could lose $1. Okay, that the expectation of each person that bought a ticket would be a negative 0.25. Remember, the television, we said, is going to sell has a value of $750, and they sold 1,000 tickets. And if they make 25 cents on each of those tickets, that's $250. So the $750 for the TV and the gain for the people that are running the raffle, let's say, of $250 adds up to 1,000. Now, before I show the second way, I want to just remind what they say at the bottom of 270, or toward the bottom. It says, note the expectation is negative 25 cents. That doesn't mean that you lose a quarter, since you can only win the TV worth $750 or lose $1. What the expectation means is that the average loss is 25 cents for each of the 1,000 tickets sold. Okay, well, let's take a look at the other method they give us to do this, and this is directly at the bottom. This does a little bit differently. It takes the and I'll use the dollar sign here. It takes the $750 that you would win times its probability, and then it subtracts the $1 that you spent. Okay, so we're not breaking it down into two parts now. We're just taking the amount that the TV is worth times your probability of winning it, and subtracting the $1 that you paid for the game. And keep in mind, we're dealing with money here. So it again would be 750 over 1,000 minus 1. And it's money, of course. And this would be 0.75 minus 1, and again, this is a decimal and this is a dollar. And again, that turns out to be minus 0.25 or minus 25 cents. So we get the same answer no matter which of the two ways that we approach the problem. Anyway, I want to make one more observation, and at the bottom, or toward the end over on toward the bottom of page 271, they tell us that in gambling games, the expected value of the game should be 0. If it's a fair game, the expected value of X should be 0, and that will help you on one of your homework problems. Okay, again, this is just something to round out the picture that we've seen on probability distributions, and I'd like to remind everybody that this is the RE to 5-3, which is one of our more interesting topics, the binomial distribution. So that's all I have to say on this topic, and I'm again crossing my fingers that these recordings take this time and don't get lost. Thank you.